Good morning, everyone. My name is Shigeki Inoue. I'm working in Hebrew University of Jerusalem as a postdoc of Abishai, and today I'll be talking about disk instability, on this talk. So I will talk about tumor instability, tumor analysis in cosmological simulation first, and later I will talk about isolated simulation. So disk instability analysis. So, I may be able to skip the introduction, but I'm now working on Clumpy galaxies. So these Clumpy galaxies are thought to be in unstable state in tumor analysis. So these Clumpy structure, so to be a consequence of the disk instability. So these galaxies are thought to formation stage of these galaxies. These are thought to be looking face on, and these are edge on these galaxies in formation stages. So these galaxies have clumps, giant clumps, the mass of which is roughly 10 to the 9 solar masses at the largest. Okay, next, this is the observation of high-redshift clumpy galaxies done by Genzel et al. 2011 with Candile's observation. So they determined H alpha map here, and the Candile's map is a 2D spectroscopic observation, so they can simultaneously determine velocity dispersion and the rotation curve of the disk. So they can observationally determine Q distribution in 2D map like this. So this is the color code indicates a Q value on each pixel here, like this. So the observation indicate that the high redshift clumpy galaxies shows Q lower than 1 in entire region of the disk regions. So next sample is here. So in observations, so how redshift galaxies indicate Q lower than 1 in entire region of the disk except the bulge region. So the clumpy disks typically have low Q. So we can say that tumor instability gives birth to clumps. Okay, so today, I'll be talking about cosmological simulation. The simulation is also a powerful tool to investigate the clumpy nature of the high-redshift galaxies and the formation process of the clumpy structures. So I used the cosmological simulation done by Daniel Severino with ARP code. So this simulation has resolution of 10 parsec order, and the radiation pressure was included. So the good point of the cosmological simulation is that cosmological simulations are always nonlinear. So I can look into the nonlinear effect of the clumpy formation. This is a great difference from the isolated simulation. So I performed cosmological simulation with tumor analysis. I picked up this galaxy. So this galaxy, large-ish galaxies at this redshift. So I'm showing stellar density, gas density, star formation rate in phase zone and edge zone here. Okay, how to determine tumor Q in my calculation? I employed the two-component model of Q calculation proposed by Romeo and Wiegand 2011. So this method divides the volume component into gas and stars. But I consider stars younger than 100 mega-year are considered to be gas because kinematic state is similar to gas rather than old stars. So, I can determine Q separately for gas component and star component, and I can combine the gas Q and the star Q into the two-component Q value. And a copper epicycle frequency is determined from actual rotation velocity. Okay, and next I remove the bulge stars. So because bulge is not disk, so I removed bulge stars according to this threshold of the rotation velocity. And I applied Gaussian smoothing to all physical quantities, density and rotation velocity, velocity dispersion. Anyway, all quantities I applied Gaussian smoothing. the FWHM of H is 1.2 kpc. This nearly corresponds to the clump size. Okay, this is a result, not result. These are the 6 ingredients of the Q calculation. The gas and the stars. Capital sigma means a surface density, smoothed surface density, and smoothed velocity dispersion, and smoothed epicyclic frequency in 2D map distribution. Okay, I can combine these 6 ingredients into Q distribution. So my calculation is like that. So, so the color code indicates Q value in log scale. Blue color indicates Q lower than 1. The blue color means so in these regions linearly unstable. Next, green region corresponds to Q between 1 and 3. This green color corresponds to a nonlinear instability or dissipative instability. And yellow, red, and green region correspond to Q larger than 3. So these regions are supposed to be stable in tumuli analysis. So and the gas Q and the star Q and 2-component Q is like this. So in the outer region, gas component is dominant over the stellar component. So I can say that our instability in outer region is caused by gas instability, not stellar instability. But at the central region, so gas Q becomes dominant. So because there is anyway, so and the 2-component model is here. So and it's interesting to compare with this is unsmoothed gas density map. So I can find giant clumps, for example, here, 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 here. Okay, these are clumps. And in 2D maps, the clump positions are here, 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 here. So the result is that my result is showing that Q becomes lower than 1 or unstable only inside the clump or around the clump only. Interclump region or generally disk region looks stable in this calculation. So the color is generally yellow or red. So these yellow or red are supposed to be stable. But clumps are actually forming. Okay, next. So this is next snapshot, different snapshot. The galaxy is the same, but lower redshif, redshif 1.17. So in this time, the disk becomes still dominant. Gas fraction becomes lower. Okay, same thing. So in this galaxy, so stellar component becomes dominant. The instability may be caused by stellar instability. So anyway, the 2-component model is like here, but the result is the same. The unstable region can be seen only in the clump or around the clump. Sorry, this is a gas map. So I can find clumps here, 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 here. But the interclump region, so this region is generally stable in tumuli analysis. So that color is generally yellow. The state is supposed to be stable, but clumps are forming actually. Okay, so next one. So this is the case of the lowest Q in galaxy I have ever looked into. So this galaxy is very, very high redshif to 4.56, and disk size is very small, 1 or 2 kpc. Okay, and the Q map is here. The Q map looks green. Green color corresponds to nonlinear or dissipative instability, but generally Q value is higher than 1, supposed to be stable. But we can find clumps here, 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 here. Okay. Okay, next one. What about in isolated simulation? So Andy has already shown, but so yeah, it's interesting to show the same calculation in isolated simulation. So the data was provided by Frederick Bonneau, and I used this simulation. So, and this simulation was done by Ramsey's code. So numerical simulation is now different from the cosmological simulation I previously showed. So the resolution becomes much better. Okay, and the initial condition of this isolated simulation is almost the same as on this simulation: exponential disk and bulge and hell. Okay, this is the result. The same calculation was performed for the isolated simulation. This is the gas map and the Q map. So we can find many clumps in this simulation, like on this simulation. But true value indicates unstable regime only in the clump or around the clump. In the clump region, for example, like here, looks stable. Q value is much higher than 1, typically 3 or 5 or something like that. Because after clump formation, this region becomes empty. Empty means much lower gas density around than clump region. Okay, and next snapshot. A little bit later snapshot, but result is the same. Right there, one more snapshot. Okay, I can say that that isolated simulation looks always stable in this region. This region is interclump region. So, okay, you may think that my calculation may be overestimating Q. So I have to discuss about this point. For example, disk thickness. So this thickness affects the calculation of Q, but generally, thickness can stabilize the disk. And I didn't apply the thickness correction into my calculation. So my calculation is still underestimating Q, not overestimating, still underestimating. And how to determine copper is different. 5 minutes, thank you. Difference between studies. So copper was determined from, in my calculation, copper was determined from mean velocity. So someone maybe determined from spherical assumption, mg over r, or something like that. Anyway, using the mean rotation for determination of copper generally leads to lower Q. This cannot be overestimation because cause of the observation, underestimation. And next, I removed the Ballisters, so I have to discuss how does the Ballister affect. So, but I found that Ballister include or exclude Ballister only affect the Q by the factor of 30% or something like that. So this cannot be the reason of the much higher tubular Q. Okay, mainly I got two main conclusions. So conclusion 1 is the inconsistency between my calculation and observation. Observation generally have shown that the Clumpy galaxy have Q lower than 1, looks unstable in the entire region of the disk. But in my calculation, numerical simulation indicates typically Q is higher than 1. Q becomes lower than 1 only in the clump, inside the clump or around the clump only. So this is probably, I think, the observations are overestimating gas density, means underestimating Q. So this is maybe because how redshift observations are determining gas density from HR for intensity. So they have to use conversion factor between HR and gas fraction. So, and another possibility is that simulations are still not good, not compatible with real galaxies. Okay, the second conclusion of my result is that Clumpy galaxy indicates generally Q higher than 1. But actually, clumps are still forming in the simulation. So the clump formation is supposed to be the consequence of the tubular instability. But actually, so Q value is not lower than 1, generally higher than 1. So, and this result is independent of the types of the simulation. I found the same result in cosmological and isolated simulations. So this is probably a criterion of the Q equal 1 may not be accurate. True criterion maybe Q3 or 5, anyway, much higher than 1. Okay, and another story is that Coulomb formation may be triggered by external stimuli. So for example, tidal force or turbulence or something like that, but I haven't fully understood yet. Okay, it's time to put the summary. Okay, thank you very much.
Questions for Shigeki?
Sorry, difficult name.
Yes, Steven.
What's the effect of the radiation pressure on the overall Q that you get from this?
Yeah.
Does it make a difference?
I have done my calculation generally for radiation pressure included calculation, but I did the same calculation for example, low, so excluding radiation pressure simulation, something like that, but the result was the same generally, so Q was higher than 1.
So how much of your clumps, how many clumps are rotating and how much are they rotating? Are they rotationally supported by internal rotation?
Rotation means spin.
Yes, centrifugal force basically. So how are they supported by internal turbulence?
Yes. Sorry, I haven't.
So actually, the clumps are then like little mini disks themselves. So the question is, do they fulfill internal? Yeah. But the question is now, do they fulfill the internal Tumor criterion? So if you just look at their internal properties, are they like little disks which have a tumor Q? You say the Q is larger than 1, but if you really look in details,
Okay.
are they like disks themselves? Thicken this.
No.
This is according to Henry. The formal domain stability indeed deals with a ring with axisymmetric. But you could view the Q parameter as telling you about the local conditions for formation of a clump. Because the Q parameter is just the ratio between forces, if you that want to create a clump by gravity. That's the surface. And the two terms that try to prevent this. The pressure, in our case by turbulence, and rotation. And in our case, which is the kappa parameter. And the competition between those determines whether you can, if you take this interpretation of your parameter, it does tell you something for your thought about the instability. Although I agree that globally this, they are never in the linear machine as Shigeki said. So we have to think about the nonlinear instability mechanisms that give you the mass function of the clouds and so on.
Okay, one last question.
So, just to comment on the Q criterion as a criterion for whether bumps should be there. It's only true that you won't form bumps in a Q greater than 1 disk if you're talking about the thermal Q being greater than 1. If it's supersonically turbulent, and you're using the turbulent Q, then even if Q is 1,000,000, you'll still form formally self-gravitating clumps. Now, if Q is 1,000,000, the disk will explode. But in the process of exploding, you'll get shocks that create regions that are technically self-gravitating.
Yes.
You can show formally, you assume the disk is confined, that if it's supersonically turbulent, there's no Q at which the disk never forms self-gravitating clumps.
But if you look at something stellar instability, if Q is around 1 is good to 10, so why do you say
So I still think Q around 1 is a very useful criterion, and that disks do self-regulate there, because Q greater than 1, the disk starts to blow itself apart, basically, even when if it's a turbulent Q greater than 1. But working with. Generates very large density fluctuations. Supersonic turbulence generates logarithmic, exponentially large density fluctuations. Whereas the turn rate Q of the disk only goes up linearly as you increase the turbulent velocity. But the magnitude of the biggest density peaks that you generate goes up exponentially as you increase the velocity in an isotropic disk. So you always generate higher density peaks than the locally self-gravitating as you increase the turbulent velocity spur.
I think we'll have to continue the conversation